Hello, everybody. Rhetoric&Discourse here again. Now, for the last week or so, I happened to bump into flat earthers. Now, this is a group of people who, while I understood that they existed, they never seemed to actually be real to me, so I mostly ignored them. But as the last week has shown me, they are not just a group of people that do in fact exist, but they are relatively popular, having several thousand views on their videos and having their ideas spread fairly wide. Now, this to me seemed slightly concerning, so I decided to take a look at some of the ideas that flat earthers sort of present me and try to see if I could use some of my critical thinking and skepticism skills to dissect the ideas. Now, the first problem that I bumped into is the fact that flat earthers don't really have a working theory. They don't really have a model of any sort for what a flat earth universe would look like. What they have instead is claim after claim after claim of garbage, really, that they just throw at you and making it kind of difficult to dissect it all, and you end up in this crazy juggling game where you're trying to deal with one claim after the other. Very reminiscent of young earth creationists. I decided to take a handful of the hypotheses that they make of how the universe should work and test them out. Actually, put them through the ringer, put a little bit of math to them. Now, the reason that I'm testing out these models is not necessarily to debunk them. Rather, I'm testing them because good models of reality should be capable of making predictions. We use good models of reality all the time to make predictions about when the sun is going to set, when it's going to rise at a certain time, in a certain place, at a certain time of the year, and they function well. So if Flat Earth wants to compete with the quote unquote traditional globe Earth model, then it needs to compete at the same level. It has to have the same amount of predictable capabilities that the globe model has. And if it doesn't, then it needs to be thrown out for the better model, the one that has the ability to make predictions about the future. And thankfully, there are actually a couple of models that exist of how a flat universe should function more or less. They're not very good and they're very wishy washy. Everyone who presents these models sort of having a different opinion on how the model works. But we'll see what we can do with what we have. Before I get too far, I want to remind everybody about this great picture here, and I'm pretty sure most of you have seen this picture at some point or another in your algebra book. This is how most of us learn to work with triangles. Now, in this particular case, we are going to be looking at one equation, which is the tangent of x is equal to the opposite side over the adjacent side. Now, most of you probably did this when you found the height of a tree, looked at the top of the tree, figured out what angle you were looking at, measured how far you went from the tree, did a little bit of math, and found out the height of the tree. Now, we'll be using the same principle for most of the equations that I have here, which is actually going to make it very easy. Now, the way that we're going to use this equation is that on a flat plane, we have a sun and an observer. As you can see here, the sun's in yellow, the observer is in blue. We'll be able to use the height or the altitude of the sun as our opposite side on our triangle. For the adjacent side, we'll be able to use a line that goes from the observer directly to the base of where the sun would hit if it were sitting right on the floor and not at a certain height. Lastly, of course, we'll have the hypotenuse, which will be between the sun and the observer in a direct line. We'll do that once. I promise it won't get too complicated. In order to test the hypothesis that flat Earth is present, we're going to pretty much get rid of this tree and stick a sun in instead. Let's see how we can use our equation to find out some information about the sun on a flat Earth plane. The first thing we're going to do is we're going to find the angle in which we will see the sun on the horizon. So, according to flat earthers, during the months of September or March, we should see a sun around the equator. I picked to put my sun somewhere around Ecuador. Now, an observer somewhere in North America, we'll put him right there, will see the sun directly south at a certain angle. To find that angle, we need to find out what this distance is. Now, I have actually taken the time to find out what the distance is straight north from the equator, and it happens to be, to this point, about 3,000 miles, and this is going to be a very convenient number for us. So going back to our original picture, now we can actually start sticking in some of the numbers. The first number that we're going to put in is the altitude of the sun, the distance between the flat Earth and the sun. Now, according to Flat Earth Society, the sun is about 3,000 miles up in the air. So we will stick 3,000 for our opposite side. To find our adjacent side, like I said, we will use 3,000. We are going to be 3,000 miles directly north of the equator. Now that we have some numbers, we can replace a variable. So we'll replace the opposite and the adjacent side with 3,000. That takes us to an equation that looks like this, where we have the tangent of x is equal to 3,000 divided by 3,000. Now, I said these numbers were going to be convenient because it means that the tangent of x is equal to 1. So anybody who's taken any amount of math should probably remember that the tangent of 45 is equal to 1. Now, you can check this out by doing the cotangent of 1 and find out that it is 45 degrees. And remember to do degrees and not radians. So what we have learned from using this equation is that an observer in North America, 3,000 miles directly north of the equator, in September or March, should be able to see the sun at noon at about a 45-degree angle. Now, there is a very convenient way to test this out. What we have here is the motion of the sun simulator. What this does is it simulates the position of the sun depending on the month that you enter and the day. It also lets you enter the latitude that you're at as well as the exact time. The next thing about this is that you can actually go test the accuracy of the simulator on a day-to-day basis. So you can, if you're watching this during the day, pause this video, go to this website, enter in your latitude, what time of day it is, and what month you're in, and you should be able to go outside and see the sun at the position that the simulator predicts. I have found it to be fairly accurate so far, so I'm going to trust it. Alright, the first place we're going to start is we're going to enter our latitude. Now, as I said, we are 3,000 miles north of the equator, which is about roughly around 44 latitude. Now, we have stated that we would be working at around noon, and down here is where we will be able to see what degree the sun is at directly south of our little stick figure guy once we get to the month and the date. Now, remember, our prediction is that our observer should see the sun south at about a 45-degree angle. We will check all this, and our prediction says that this will happen in the month of March. So we can check in the month of March. Actually, really close. It actually changes a little bit throughout the month, so not bad. We'll double check the month of September. And once again, not bad. It changes throughout the month as the sun moves up and down, but not a bad prediction considering we were just predicting a whole month and not the date itself. Well, so far so good with our little model here. We have very accurately predicted at what angle we would see the sun rise and fall on a flat Earth model, and it actually coincides really well with reality. Now, of course, the fact that it got this one thing right does not actually mean that the entirety of the flat Earth model is correct. As we all know, a broken clock is correct 2 times a day. So let's put our equation to a little bit more of a test here. So the next thing that I want to find out is what would be the distance on the adjacent side between an observer and the base of a sun at 0 or actually 1 degree, so at about sunset or sunrise. Now, in order to do this, we are going to once again know that the height or the altitude of the sun is about 3,000 miles. So this gives us an equation where the tangent of 1 degree is equal to 3,000 miles over the adjacent side. Now we'll do a little bit of equation rearranging, which gets us to adjacent equals 3,000 divided by the tangent of 1. A little bit of more math magic, and that gets us to our adjacent, our bottom line, to be about 171,869 miles. Now that's a big number, and that is actually a very big problem. You see, in order for the sun to be 171,869 miles away from the observer, it would need to be about almost about that far away. That is how far the sun would need to sit in order to make our equation work. Now, this, even in a flat Earth model, doesn't work. It actually works a little bit better on a circular round Earth model, but even then I think I might be off by a few miles. Considering that the last time we used our equation it didn't quite line up with the flat Earth model, I actually want to find out at what degree would I first see the sun. The picture here is a model of how the Earth and the sun would function in a flat Earth model. As you can see, the sun is basking the Earth in about halfway on light and halfway in dark. Now, this I am assuming to be fairly accurate, but because, like I said, flat Earth models tend to not be very concrete, it is hard for me to say if this is actually a genuine proposed idea for how the sun would work or not. But we're going to assume that it's true just so that we can find out how, in this particular model, the sun would work. So I'm going to place myself here in the equator, where the sun should barely be rising over the east. In order for me to find out at what angle the sun will quote-unquote rise in, I need to find out what this line is. Now, in order to find out what this distance is, it's actually fairly easy because we're working with a couple of triangles. So all I need to do is find out what the distance between the sun and the North Pole is, and the distance between me and the North Pole is. Thankfully, because we are working with the equator, I can assume that the equator is about half the radius of this disk. Flat Earth Society has provided me with a number for how big the Earth is. According to the Flat Earth Society, the diameter of the Earth is about 25,000 nautical miles. I'm going to do a little bit of math and change this over to regular miles just because the altitude of the sun is given in regular miles. So that gives me a diameter of 28,769 miles, give or take some. Now, of course, to find the radius, I'm going to have to take that number divided by 2, which will give me a radius of 14,384. We'll divide this again by 2 to get the length of each side. 7,192 for each distance between the sun and the North Pole, and the observer, me, and the North Pole. Lastly, all we got to do is a little bit of Pythagorean theorem to get this squared away, and we find out that side C is going to be 10,170 miles between me and the sun, or the base of the sun, I should say. Now, in our model, we now know the distance between the ground and the sun, which is 3,000 miles. We now also know the distance between the base of the sun, I'm going to keep calling it that, and the observer, me, which is 10,171 miles, which means that we can once again use our tangent of x equals opposite or adjacent, fill in the numbers, which leaves us to the tangent of x is equal to 0.2949. We're going to do a little bit of inverse tangent, which gets us to about 16 degrees. So what does this tell us? It tells us that at morning or evening, when the sun is either setting or rising, it should actually be setting or rising at around 16 degrees. It should appear in our field of vision at about 16 degrees high and then slowly moving towards us, creating that arc that we see. Now, once again, we're going to check this. We're going to go back to our motions of the sun simulator. Now, we decided earlier that we would set this at the equator, so we'll set 0 degrees latitude. And then, of course, we have decided that the sun rotates around the Earth plane in March and September, so we'll set this to March. And then finally, let's make it to morning, just right around there. We're actually going to do the animation here at about 15 minutes, and we'll start the animation, see when we start seeing the sun peek out from the east. And there it is. It's just barely peeking out. And the sun's altitude is 0.1 degree. Okay, so this isn't quite showing us the same thing that we found in our little trigonometry. Now, what our trigonometry showed us is that we should see the sun appear at about that high in the morning at the equator in March or September, and that is nowhere near what we actually see. Now, that didn't work out as well as I thought it would. That's alright. I'm pretty sure flat earthers will have a really good excuse for this. My guess is that they're going to tell me it has something to do with light refracting. I'm guessing the flat earthers will tell me that the sun is in fact 16 degrees up from the observer, but it appears to be in the horizon because light is refracting. Now, that actually isn't too bad of an ad hoc explanation, but if you're going to do that, you're no longer allowed to do this. You are no longer allowed to use this. You are no longer allowed to use the rays of the light of the sun come in from various directions, showing that the sun must be closer. Because if you're going to tell me that the sunlight is being refracted in the atmosphere to spare those 16 degrees, then you understand that light gets refracted by clouds and can come out in all sorts of very fun and interesting angles. Now, another thing that I've noticed a lot of inconsistencies with in the flat Earth model is the shape of the sun. You figure this is something they'd have figured out by now, but they really don't. As we look at the sun in the sky, we notice that from every angle, no matter where we look at it from, it is always a circle. A sphere is the only shape that achieves this kind of perspective, where it can be seen from anywhere and always look like a circle. More important than the shape of the sun is actually how it emits light. Now, if it is a sphere emitting light, it would emit light in an omnidirectional way, emitting light rays in all directions. This, however, very much so contradicts the explanations or the models given to us by flat earthers. One flat earth model has something like this, where you have a spotlight running across the earth, and even that spotlight you can see is not quite covering up the whole area that it should. It doesn't actually account for the half of the earth that is in sunlight throughout the day and the half of the earth that is in dark. A model that is closer to this would actually take care of that. Of course, the problem with spotlights is that they cast shadows in circles. So if the sun is in fact a spotlight, we would expect that the shadow that it casts to be circular rather than half a line running down the dish that is Earth. The other problem that we see with spotlights is that if we view them from any other angle besides directly underneath, they don't actually look like circles. They start looking more and more like ovals. Here we can see that as we scoot on over underneath the spotlight, it looks like noon. But as this spotlight sun starts setting, we can see that it loses that circle shape, giving us more of a oval shape. On the other hand, if the sun is a sphere, we now see that from underneath at noon it is a circle, and even as it starts setting or moving away from us, it still keeps that circular shape. What we have here is we have flat earthers who are telling us that the sun has to both be a omnidirectional light and a spotlight at the same time, and yet these two things cannot exist together. So someone who has a flat earth model really needs to explain this to me. How can you have a spotlight that can be seen as a circle from all directions? Or how can you have a spherical sun that produces light in a spotlight fashion? You can't have both. And if you can, you need to explain to me how the mechanics of this works. One of the strangest things that I have found in the flat earth models is the way that they see stars. Here, I'll give you an example. As you can see by this wonderful illustration, looking down at the dome of the Earth, the stars should rotate counterclockwise. So if we have, for example, the square constellation to the top of the dome and a triangle constellation at the bottom of the dome, after a few hours, I suppose, because nobody gives you times or numbers to, test these models, the constellations should be entirely flipped. Let's change perspective here and give you a different idea. If, for example, I am sitting at the bottom of Africa, I can look straight southward or towards the rim of the Earth and see my square constellation. As the night progresses, I should therefore then start seeing the constellation head westerly and be replaced by a new constellation, my triangle constellation. This is one of the predictions that can be tested in a flat Earth model. So we can see if we do in fact see this kind of stellar change when we look at the stars. All right, what we have here is the Planetarium web app. It's part of Neve. I will put a link in the description so you can go try this out yourself. And what this little app does is it lets you see what the stars would look like on a certain day. You can pick the year, the date, the time. It's pretty nifty. You can even change locations and really get a good handle of if you were to look at the sky at a certain time, what you would be able to see. So let's try out our experiment here. I don't think the date is going to matter too much because it should be happening on a 24-hour cycle. And we're going to place ourselves, like I said, at the bottom of Africa, and we will make ourselves look directly south. All right, and we won't actually look at the celestial south, we'll look directly south. And here's a nice little constellation that we can keep an eye on, this triangle constellation here. So remember, from our model that we were given, we should see the stars go from east to west, and we should just see them all move across, and eventually we should lose this triangle constellation and it should be replaced by another constellation, potentially maybe one of these constellations over here. And let's see what happens. We'll go hourly. Well, we can already see that our constellation isn't moving east to west. It's in fact moving upwards and east. That already doesn't match up with our prediction. And as we keep going through the night, what actually ends up happening is our constellation is back. So we haven't even gone a whole 12 hours, and our constellations just rotated. They didn't move east to west like the flat model would predict. Alright, so let's check out what other things flat earthers have to say about stars. The fuck? Wait, did I read that right? Are you saying that astronomers are telling you that the stars should head west to east if you're in the southern hemisphere? I hope you understand that if that were the case, that the sun would do the same thing. The sun would head from west to east in the southern hemisphere, but head east to west in the northern hemisphere. And that is, well, plain old wrong. So, I don't know what scientists you're talking to, but you need to ask for your money back. Alright, this last claim here was a little weird. And I couldn't quite understand it. The best that I could do is, well, I came up with this as what they meant to do. Alright, let's head back to the planetarium and test out what I think is what they mean with this claim. So we're going to change our location to the northern hemisphere, so we'll go to North America. And we are actually going to be looking this time at celestial north, which is right there. Now, I think this is what they mean by the claim, but I'm not 100% sure, which is that if you are looking at celestial north, the stars should turn counterclockwise throughout the day. That's the first claim, so we can check that out. We'll make this go an hour at a time, and as you can see, it does in fact, the stars do in fact do a little cycling motion counterclockwise. Perfect. Now, the corresponding claim is that the stars, if you look to celestial south, the stars should turn clockwise. And that is the claim that astronomers make. The video then says that this isn't actually true and it's overtly exaggerated. So we can find out. We'll head back down to the southern hemisphere. We'll find celestial south. There we go. And we're going to do the exact same thing, move time forward, and this time, according to astronomers, the stars should turn clockwise. So let's see if we can see that. And in fact, we do see the stars turn clockwise. So where do flat earthers get this idea that stars do not turn clockwise in the south, and they is beyond me. So someone needs to explain that one to me as well. So some of you may be asking why I am bothering to do this video. Why would I ever bother to look at a group like the Flat Earthers and debunk or try to critically analyze the shit they peddle? What I would like to think is that Poe's law is into effect here, and I am really just looking at a bunch of trolls that are out there having fun. But there's a very cynical part of me that understands that that's probably not right. Now, part of me is very cynical and knows that there at least is a small group who buys into flat earth theories in a very genuine way. So for those that are not posed in the flat earth movement, I hope that this video will help them question their model of the universe a little bit. I don't expect this to change anybody's mind. I just expect it to have them skeptically look at their own beliefs. Now, the other reason that I decided to make this video is because of this asshat, Jeranism. Jeranism is a slimy son of a bitch. He promotes flat earth plus a whole bunch of other crazy conspiracies, and he does it incredibly dishonestly. So after watching a lot of his content, I decided that flat earth needed to be talked about. Now, the problem with talking about flat earth is that there are two different ways to approach it. One way is to approach it from a scientific, logic-based point of view, which is what I tried to do in this video. I tried to take the claims that they are making and I tested them out to see how well they held up to the model of reality that we see every day. The second way to talk about flat earthers is to talk about the rhetoric that they use. How do they talk about flat earth ideas? Now, that I'm going to save for a separate video, and that is probably going to end up talking about Jeranism a whole lot because, like I said, he's one slimy fuck.